Hello everyone, let us understand the concept of confidence interval. So what I'm trying to explain here is the concept of confidence interval. And fundamentally, if I talk about confidence interval, it comes under theory of estimation. It comes under theory of estimation. And means you want to estimate certain things by using an interval or by using point estimation. So let me straight away jump into a particular example and let us understand how exactly we can estimate certain things by using the concept of standard error and sampling error or margin of error. Think about a particular example that I am saying that in a university or in a college there are probably 1,000 students. So I have got capital N, that means in total there are 1,000 students are there. And I do not have access to their entire database. I have access to certain samples. In order to estimate that if there is a test of statistics which has been taken and the maximum marks of the tests are 100, then what could be the possible average marks of this entire class? So if I want to understand that and I do not have access to all these 1,000 students or something like this, just understand it diagrammatically. So I've got, let's say, 1,000 students here in this entire universe of my study. When I say universe of my study, I mean the students who are studying this particular course of statistics. And I do not have access to all the 1,000 students. So probably I'll take a sample of first sample of, let's say, 100 students and I calculate their average marks. So I'm writing it X and 1 bar and I probably find out that their average marks are 51. And I can make certain estimations that if average marks of a sample of size 100 is 51, so I may end up saying that the average marks of the entire population, which is represented by mu, let's say. So I'm saying that I can probably try to estimate something that mu, which is representing average marks of all 1,000 students, are also equal to 51, and that I will call as a point estimation. Now you can definitely improvise on this point estimation by taking several other samples. So probably I'll take another sample N2 and that may be of same size or a little different size, let's say of 120 students. And I try to find out the average marks of these 120 students and it comes out to be somewhere around, let's say, 53. And then probably I'll take up an average of xn1 bar and xn2 bar and I divide it by 2 and that comes out to be 51 plus 53 divided by 2 and 104 divided by 2 and it comes out to be 52. And again I try to estimate and I try to make an estimation that average mark of the population is actually 51, 52. That means this time I'll make another this arrow should go here. Then that means I'm saying the average marks of the population of 52. So this is again a point estimation, right? So I can further improvise it. I can take 3 samples, 4 samples, keep on doing it. That is one way I can do that. And that particular thing is called as point estimation. Other thing what I can do is I can pick up a sample, same way I can take up a sample. Then I take up the sample average. I probably assume the standard deviation of the entire population marks. And let us suppose the standard deviation is 12 marks. I'm assuming it for now, just to stick with this thought, and we will be further discussing it, that how I can take an actual standard deviation. And depending on these three observation, number of units I picked up for sample, the average of the sample, and assume the population standard deviation, I can probably, kind of make some estimation that average marks of the entire batch of 1,000 students on the basis of this sample information is somewhere between, let's say, 48 to, I would say, 54 marks. I will definitely be talking about these calculations of 48 and 54. that how does these things appear. And if I say that, okay, listen, I have taken a sample of 100, the sample mean is this, and there is a standard deviation which I've assumed for the entire population depending on my observation or something, and I conclude that the average marks of the entire population is going to be somewhere between 48 and 54. So the difference between this estimation right here on the top, which I did before, and this one, which I'm doing right now, is that here I'm actually trying to predict something within an interval with lower limit and upper limit. So this is lower limit of the interval, and this is definitely the upper limit of the interval. And I would call it as interval estimation. Interval estimation. So it is, pretty much visible that interval estimations have a higher tendency to be correct. And if I add something more to it, let's say I write probability of this to happen is whatever, let's say 0.95. Or I say there is a 95% chance that the population mean falls between the marks of 48, 48 and 54. That means the entire population mean is going to fall somewhere between 48 and 54. And the probability of this scenario to occur is 95% or 0.95. So then I have higher chance of making a correct statement. So this is exactly a fundamental concept of interval estimation, and how do we create an interval estimation? That is going to be the major point which I will be discussing here. So I'm going to talk about interval estimation, and that you can also call as confidence interval. Why? Because why I'm calling it a confidence interval? Because I estimated an interval with the confidence which was 0.95. So probability of this to happen is 0.95. So I'll call it a confidence interval. Well, you can create these confidence intervals in two ways. That means if the one is when the sample is large, and the sample is large, and then when I say large, I simply mean that it is greater than 30 here. And then standard deviation of population is known, which is an unrealistic condition. I understand that. But for now, let us assume that something like this can happen, and we can probably in the other videos I'll be discussing the concept of center limit theorems or large samples. So standard deviation of population is known. So these are two conditions. If these two conditions met, is known, and in some cases I'll assume it also that is to be given by sigma. In that case, I'll be using a z distribution to calculate interval estimation, to construct an interval estimation, or to develop a confidence interval. And the formula for this is going to be something of that sort. Probability that x bar minus z alpha, and now it is going to be standard deviation of population divided by square root n is less than equal to mu is less than equal to x bar plus z alpha sigma divided by square root n is equal to 1 minus alpha. So you understand that alpha is a level of significance, and you can see the videos on normal distribution of mine to understand what is level of significance. So alpha is level of significance, sigma is standard deviation of population. I mentioned it. X bar is going to represent the sample mean, and this is the sample size. So all the terms are known, and mu is the population mean value which I'm trying to estimate. So x bar here is actually sample mean. It's a sample mean. Z alpha here is z score at alpha value, whatever alpha is, and I'm going to fix it from point 0 to, I'm going to fix it at 5% or 0.05 for some problems, coming problems. It is sigma is standard deviation of population, of course. And if you see, n is simply sample size. Now, other way around, if I think about the second particular case, in this case, when the sample is small, it means I'm taking something less than 30, and standard deviation of population is unknown. And here I'm going to use a t distribution instead of z distribution to develop my confidence interval. And that particular interval will be given by probability of population mean falling in these two values, x bar plus t alpha sigma divided by square root n. I'm running out of real estate. I'm going to put it here 0.95. So what I mean to say is only z value is replaced by t value here. Rest of the formula remains same. Oh, I did a mistake here. The population standard deviation is not known. So this would be small s. That means the sample standard deviation. So this would be a small s. Let me just rewrite it. And so I'll just clean it up here. And I'm going to put something called small s. That is the sample standard deviation. Now, in this entire formulation and everything, what do I understand is that sigma divided by square root n is called as standard error. Just put that like this. Standard error, also called as sampling error. While if I multiply it with a z-score or t-score, so this, or I would say t alpha s divided by square root n, is known as margin of error. Or you can also call it ME, and this is called standard error, so you can call it SE. Let's build up a quick problem. Let us understand how do we solve a problem of some kind. So let me take up a quick problem, and I am saying the same problem, and the sample is 100 students, and I have calculated their average marks of the sample, and that is given by, let's say, 52.18. And I've assumed the standard deviation of the population, which I'm representing by sigma, is, let's say, 25 marks. Now I want to estimate that what is going to happen with, or where the mu is going to fall. What will be the value of mu? In what limits the mu is going to fall? Since I know the sample is large, standard deviation of population is known, so I'm sure that I'm going to use a z distribution for this interval estimation. Let me set up an alpha value of 0.05, and z-score at 0.05 is going to be 1.96. So yes, how did this 1.96 has appeared? You can check the videos of mine for normal distribution, how this z-score at 0.05 is 1.96. Let me quickly create an interval. So I'm going to create an interval probability that it is going to be with x bar minus z alpha, and it is going to be sigma divided by square root n less than equal to mu less than equal to x bar plus z alpha sigma by square root n. Since alpha is 1.96, so 1 minus alpha, I'm going to put it up here. So alpha is, okay, let me just check one thing. Yes, I did it. So let's go ahead and let's solve it out. I know my values. X bar is going to be 52.18 minus z alpha. I've already calculated it 1.96, and that is going to be sigma, that is 25 divided by square root n, which is 100, and that is less than equal to mu, less than equal to x bar, again 52.18 plus 1.96, and again a sigma value of 25 divided by square root of 100, and it is 1 minus alpha, so 1 minus 0.05, or I can write it 0.95. If you calculate it, then I'm going to get something of this sort. You use a calculator, calculate it, this term, becomes 2.50, and 1.96 multiplied with this becomes 4.90, and you're going to get something of this sort, 47.28 less than equal to mu, less than equal to 57.08. So this is in 0.95. And how do you conclude that? That probability of that the population mean is going to be between 47.28 and 57.08 is 0.95, or there is a 95% chance that if I randomly pick up a student, then his average marks are going to be between 47.28 and 57.08. On the other hand, if you want to understand or through sample way round, then you can call it that probability that you know there are, if you start picking up samples from this data of 1,000 students, so I know there are 1,000 students, and you start picking up samples, then 95% samples will be having the population mean within them. So that's another way to conclude it.